climate is one of the most fundamental drivers of ecological condition. We've heard that quite a bit throughout the morning. For the Central Alaska Network, there's pretty strong climate gradients, and which are intrinsic to the ecosystem patterns that you find in the parks. The vegetation communities and the animal communities follow these gradients, and therefore any changes in climate will in turn have a tremendous impact on these communities and these ecosystem patterns that we find. So the objectives of the climate monitoring program for the network are to monitor and record climate conditions at representative sites in the 3 parks so that we can provide good, reliable climate data to scientists and the research community, and so that we could start to just refine some of the climate models that are coming out of the state. There are 3 major climate regimes within the Central Alaska Network. Along the southern coast of Wrangell-St. Elias, we've got a maritime climate influenced by the Gulf of Alaska and the Pacific Ocean. As we move inland through the mountain ranges, we find transitional climates, and then as we move further inland, away from the influence of the ocean, we find the interior continental climate. This is a map that shows the mean annual air temperatures around the Central Alaska Network, with 0 degrees Celsius being in yellow. So you can see some of the areas along the southern coast of Wrangell-St. Elias and some areas south of Denali are right at that threshold of 0 degrees. Yukon-Charlie Rivers is in the northwest area of the Central Alaska Network. It's a true subarctic interior climate. The mean annual air temperature, the MAAT, sorry for the abbreviation, is below freezing. The wintertime temperatures are strongly controlled by inversions. And most of as far as the observed climate for this area, it came out of the long-term site at Eagle. And when we talk about long-term climate, we're generally talking about the climate of the valleys. There weren't any sites in the upland areas. So one of the goals of the Central Alaska Network was to get more representative sites in these parks. So we put a station up in the Upper Charlie River and the Tanana uplands to try to fix that and fix some of the models. The long-term station at Eagles provides a pretty good baseline. The average annual air temperature is 25 degrees, total precipitation is about 12 inches a year, and the total snowfall is about 56 inches at Eagle. For Denali, there's 2 pretty distinct climate regimes with an obvious geographic barrier being the Alaska Range. We've got a maritime transitional climate south of the range, and then a continental climate in the northwest area, and a bit of a transitional climate right around park headquarters. We've got a long-term data set at the McKinley Park site. We've got over 80 years of information from that site. Average annual temperature is a little bit warmer than Eagle, 27 degrees. Precip's about the same at 15 inches, and snowfall total is 81 inches. And in the past few years, we've tried to get more sites out at representative locations in Denali. So we're looking at higher elevation sites and a better geographic coverage. In Wrangell-St. Elias, it's obviously the most climatically diverse. We've got the coastal region, the transitional, and the interior. Pretty exciting place to monitor climate, but it's also pretty daunting. It's 13 million acres. It's got 4 major mountain ranges and large river systems. So we took the transect approach in this park and used this north-south transect, kind of cutting through all the mountain ranges and placed climate stations along that transect to try to pick up some of the gradients. It's pretty interesting if you look at the northern regions of Wrangell versus southern regions of the Wrangell area as far as long-term temperatures and precipitation amounts. This is Salina up here. Average air temperature is 27 degrees versus Yakutat with an average air temperature of 39 degrees. Total precip is about 15, same as the other continental interior sites, and snowfall's at 55. And then we look at the precipitation at Yakutat, and we see that it's quite a bit different, 145 inches, and total snowfall at 189 inches. There's a couple long-term sites within the park that we can use for good baseline averages. We've worked pretty hard over the past 4 years to develop this program. We've put in 15 new sites around the 3 parks, including 2 snow-tell sites. We've developed protocols And we've initiated critical partnerships with the National Weather Service, Western Regional Climate Center, and the Natural Resource Conservation Service. And these partnerships are going to be the key to the success of this program and the longevity of it. So how do we use this, use the information? The long-term sites within the network provide the context, provide the baseline averages, and the new sites provide better coverage, better spatial coverage, and better elevational coverage. Recently, we had an analysis done for the long-term sites within the network by Dr. Richard Keene out of the University of Colorado. And the next slides are just going to go over some of the results of the analysis. For temperature, we looked at 95 National Weather Service cooperative observation stations. The period of records ranged from 1 to 105 years. Out of all these sites, there were 8 stations that had long enough records that we could calculate mean or 30-year normals for, and 18 of the stations had records that we could go back before the normal, the 30-year normal, the current 30-year normal period, which is 71 to 2000. So we can go back prior to 71. Some of the stations were combined with other nearby stations to create longer records, and between the long-term stations that existed on their own and the combination of stations, we generated 9 time series that were greater than 80 years for the Central Alaska Network. This graph just shows latitude on that axis and longitude on the x-axis, and these are the sites and how they're dispersed within the Central Alaska Network, with the McKinley Park site being there, Canadian border being just about there at Dawson. So when all of the temperatures for all of these 9 sites were combined, we looked at how they worked out as far as departure from normal over the year from 1900 to 2000. And they correlated pretty well amongst each other, but as far as departures from normal, you can't use, you can't compare like Eagle temperatures to Yakutat, obviously, so we did departures from normal. What's interesting to look at in this graph is this sudden shift in 1976 where it was going along fairly stably, and then all of a sudden it shot up. A lot of times we use climate indices to try to explain what's going on when we see variations like that. The Pacific Decadal Oscillation was talked about a number of times today in other talks, and Sandy just alluded to it. It's an index that measures the strength and the persistence of the Aleutian Low within the Gulf of Alaska. And there's been 2 major shifts in the PDO, one in 1947 and one in 1977. The 1947 and 1977 was the cold regime, and then it warmed up significantly after 77. And the temperatures that we've seen for the past like 30 years have been part of this warm phase of the PDO. In the cold phase, the Aleutian Low is a fairly weak state, so the Arctic air mass kind of is centered over the state, and the winter temperatures are colder. In the warm phase, that Aleutian Low kind of pushes up further into the state and brings a lot of that warm maritime air into the state, and it persists pretty well into the southern areas of the state and into the subarctic region just a bit. It doesn't explain what's going on in the Arctic, though. I'm kind of focused on the Central Alaska Network and not really the Arctic. That's under a whole different, can't even go there. Don't know about the Arctic yet. Oops, wrong way. This just shows the persistence of the PDO as it relates to the December, January, and February wintertime temperatures and how far it persists into the state. And you can see that Yukon Charlie is about right here, and it's definitely affected by this PDO influence. If you look at the annual temperatures for those 9 long-term sites during the 3 regimes, you can see that during the first warm phase, it was 31.7 degrees Fahrenheit, and for the last one, this last 30 years, it was 32. So the difference between those 2 is not all that much. But if you look at the abrupt shift in 1976 from 29 to 32, that's pretty significant. So although the average is, it seems like it's warming over the past couple decades, actually it hasn't warmed as much as one would expect, or as sometimes is referred to in the literature, if you look back farther than the 1976 shift. These are a couple of graphs from the Alaska Climate Research Center, just kind of highlighting that fact. This shows 1949 to 2005. If you put a trend line here, it looks like we've had a pretty significant warming. This shows 1976 through 2005. Pretty flat line and not much of a trend. So the period of record analysis is pretty important. In summary, the major control of the variations of the Central Alaska Network average air temperatures appears to be the Aleutian Low and the PBO. Baseline averages between the regimes bear little semblance from one regime to the next, so you can't really talk about a trend. And the change between the regimes has happened at least twice in the past decade, or past 100 years. Excuse me, 100 years. So the use of trend analysis in climate change research really depends greatly on what time period you pick. Other indicators of climate change are extremes. We talk about decadal oscillations, but extremes definitely have an effect on ecosystems. These two charts show temperature departures for the warmest recent year on record, 2002, at the 9 long-term sites. And this one shows the coldest year on record, or coldest recent year on record, which is 1996. This one shows the warmest summer on record, which is 2004. Oops. There we go. The warmest summer on record, which was 2004. You can see the temperature departures from normal. These are temperatures above what you would expect for each of the 9 stations. This warm summer also happened to have one of the shortest snow seasons on record, 2003 to 2004, where we had snow melt in April, snow off ground in April, and it was also one of the largest fire seasons on record. So you can see how it's kind of like a domino effect, just based on seasonal variations. For precipitation, we don't quite know as much as we do for temperature. Precipitation data in the state is generally pretty poor. The most consistent long-term record we have is the NRCS SNOTEL sites. And we looked at, for the analysis that Richard Keene did, he based it on the 61 snow courses around the Central Alaska Network. This chart just shows, the McKinley Park station is an exception to that rule. The co-op site has been run for 80 years, and it has pretty consistent data. This is from September 2005 through August 2006, and it's the departure from normal for precipitation. You can see our wet summer in there, about a ½ inch more for June, July, and August than we would expect. There wasn't a very strong correlation with any of the climate indices, and this just is highlighting the PDO with snow water equivalents from those sites. So the results from the analysis. It's not working.
No, we're done.
We're done?
Sorry.
Results. Best correlation is between the winter temperature and the winter PDO. Summer temperatures aren't significantly correlated with any of these indices. And precipitation, although the sites are coherent within themselves, they're not linked to any of the major circulation indices. The climate of 2005 is just, I just put this to highlight some of the things that have gone on in the past couple of years with the warm summers. Even though we're talking about different time scales, sometimes what happens on a year-to-year basis has direct implications of what happens in the ecosystem. So this is pretty interesting that the air temperature is the 6th warmest on record, 6th consecutive year above normal for the state, and it's the 3rd warmest summer on record. And here's just highlights between 2006 warmest temperatures versus 2005, and the number of days above 80 degrees and 70 degrees, which is it's pretty different from one year to the next. We talk about ecological implications. We're mostly talking about thresholds and how climate can change what we mostly look at is abrupt climate changes, and when we get to, when we look at that 0-degree range of temperatures and what might happen if the temperature warms just a little bit, there's implications for almost everything that was talked about earlier in the morning, so I won't go into too much of that. But as things change, especially around the melting point, we're going to see changes in the ecosystem. One thing that is an absolute certainty is that Alaska's climate will continue to change, and we're going to do our best to monitor it. And all of these data are available on the web also through the Western Regional Climate Center. Thanks. Sorry.